The installation is controlled by this 500 amp fuse switch, and in turn the fuse switch will supply this butterfly chamber, from which the whole of the installation emanates. These switch fuses here are connected to the butterfly chamber via cable trunking. The power to the factory is derived this 300 amp TNCS service, and the cables then pass through a CT chamber, and the CTs will or are supply a digital energy meter, which indicates that the power factor at the moment is 0.9 or thereabouts, and here is the power factor correction of unknown capacity. There's a broken switch on the front, and it's controlled by this switch fuse over here. Right, what I'm doing here is to record the power in this particular line, and as can be seen, the power is fluctuating continuously. The reason being that machines are going through variable loads all the time, and any increase in load on the machine will improve the power factor, and the converse is also true. But as we say, we've got no consistent power load. It's dependent entirely upon the loading on these machines, which there are a large number of. It's very important that when using the analyzer, that the voltage connections and the current connections correctly coincide. Looking at the voltage phaser that I've just drawn, we have L1 just there, we have L2 just there, and we have L3 just there. Let's assume that the current in L1 is exactly in phase with the voltage, and the phase angle is 0, so therefore the power factor is equal to 1. So let's call that I1. Now let's imagine that the analyzer connections are incorrect, and we have L3 associated with L1. What the analyzer would then see is a phase displacement between current and voltage of 120 degrees. Now, if we complete my little phasor diagram just here, this inside angle is 60 degrees, and the cosine of this angle, which is power factor, is equal to -60. The angle is rather -60. The cosine of -60 is -0.5. So it would be recording a power factor of 0.5, when in fact the current is totally in phase with the voltage, and it would lead to the presentation of false information. The test about to be conducted here is a test of phase rotation. The phases should peak one after the other, spaced out 120 degrees or 1/3 of a cycle. The sequence is L1, L2, L3, and just here we have a phase sequence tester, and when the button is pressed in the middle, the lamp on the right lights up, hopefully can be seen, and this indicates that phase rotation is correct. If phase rotation is incorrect, it will cause electric motors three-phase electric motors of the induction type to run in the reverse direction. What the analyzer is now displaying is the phasor diagram of current against voltage, and as can be seen in the fluctuations, in each case the current is lagging behind the voltage, but the angle of lag is continually variable depending upon the demand being made on machines at any particular time. As with all machines, if you start loading up the machine, the efficiency improves, and so will the power factor. And on the left hand side is a continual indication, digital indication of the line currents, and below that you've got the phase angles of the three phases, which are continually on the shift, as you can see. Shown on the screen at the moment is a bar graph of the harmonic content of current within line 1, which is at the moment around about 33% is a total harmonic distortion. Which is shown in the top of the screen. The K factor required for any transformer with these levels of harmonics is continually varying, shown at the top of the screen as well. It's a useful thing to record voltage over a period of time. This is phase voltage on this particular phase, and it's recording a value of 243 volts, but the factory at the moment is in largely a quiescent state, and everybody's having a break. Machines are largely off. When the machines come on, we'll see what the voltage dips down to, and this is an important part of assessing power quality of this installation. We shall see. I'll leave it running for maybe an hour or so. It's 238.1, and the average voltage is 240.8 volts. So we're looking at +3 approximately, -2. So they're the voltage variations that are taking place here, and this is due to loading, of course. As the cables are loaded up, volt drop occurs, and that's subtracted from the voltage available for driving loads. I need to find out the cross-sectional area of a 4-core armoured cable, which is supplying an adjacent distribution board, and to do that I'm going to use this vernier gauge, measure the outside diameter of the cable in millimetres, and then I'm going to refer the value recorded to a data sheet which will give me some idea of the size of the cable. What's being conducted here is another test of line output impedance, this time with a metal tester, and there's some discrepancy between the readings because we now have 0.13 at a location which is slightly remote from the mains. But discrepancies such as this are likely where you've got very low values of line-up loop impedance. Contact resistance can make a big difference in percentage terms.